Hello everyone and welcome back to this channel, and we'll continue with the thing that we have started in the last video with this paper that we have started. So I just felt maybe know detailed study of the paper is probably not very uh, not very desirable here, not very useful probably. So we will go through the main conclusions that they have come to, and then we'll take some notes on what we have studied here. And also we'll try to define the structure of the paper. I'll try to define what we'll be doing, what we'll be going through, more like a plan of our future of how we'll the plan of the paper, how we'll organize everything. I will go through that. I hope in this video. So let's get to what this paper has. Let's get to the other details. Other details. So we have non-domination. Let's see the definition of non-domination. Let's see what that is. I'll say define or 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 elaborate non-domination. Sorry. I'll say wait. I'll make sure I use 4O model, just because that's very powerful. I swear. I should say elaborate non-domination. I think. Let's just go through this one topic and just you don't need this, right? We don't need this. You just okay. So we have definition 3.6 non-domination. The concept of non-domination in context of uh right. So we have SF, which is the basically the visit distribution function for all the states, given across all the policies. F pi is the visit distribution function of pi. Okay, we have all the introduction. We have gamma introduction, discount rate, that defines how future planning, or how if that defines if we want the model to plan the future, or uh, prioritize immediate rewards. That is what that means. And then we have F pi of is an expected cumulative reward. Oh, so yeah, so this is the equation, right? We have this equation. Okay. Which is the function? Key point. Discount rate. Okay. Non-Bayesian function. No, if F pi is a nominator, if there is at least one reward function R and discount rate Y such that is strictly greater than the value for any other visit distribution F pi. F pi, that is hat. Okay, is non-dominated if there is at least one reward function and discount rate such that the value is strictly greater. So we want this probability to be the greatest than the other policies, the visit distribution of other policies. That is pretty straightforward, right? Pretty straightforward. Right. So that is right. Yeah, that is had some type of metric that I think measures the policies, metric for the policies. That's a pretty good word. So some actions have a greater probability of being optimal. Let's see what this is. Maybe I'll just use let's summarize this using this LLM. I'll just copy and paste it. I just put in the parentheses. Okay, space that. Let's see what is the final. Therefore, what do optimals tend to look like? Seems to depend on the one prior's belief. So yeah, you know what? I'll ask the model, right? I'll ask the model, what is the conclusion? What is the proof or conclusion of the above text, of the above paragraph? I'll just put that. Let's see what the conclusion is. So yeah, maybe this is a good uh, way of putting it. Maybe this is right. So let's see. Though the section concludes with several key points, optimal policies, and okay, section 4, right? Is that section 4? Yes, that is section 4. The title is some actions have a greater probability of being optimal. Okay, okay. So optimal policies action tendency. Optimal policies tend to favor certain actions in specific situations based on the reward function and discount rate. Okay. The probability of an action being optimal can be quantified and depends on the distribution of reward. Right. So okay. So the probability of an action being optimal can be quantified and depends on the distribution of the reward functions considered. Distribution of the reward functions considered. Okay. Right. Pretty straightforward, right? The reward function defines well, you know, the optimality of a action is quantified by the reward function. I think that is what, yeah, I think that is that is what that line means. uh Distributional assumptions impact optimality. Mm, the likelihood of certain actions being optimal is influenced by the distribution of reward functions. For example, under a distribution where rewards are independently and identically distributed across states, okay, certain actions may have equal probabilities of being optimal when gamma equals 0. So let's yeah, we might need a little distribution of reward function. Okay, so the distribution of reward functions, right? Not only one reward. Uh, right. So we have like many reward functions. I think that is what. Okay, so we'll have many reward functions, and I I think the most optimal action is the action that satisfies the most number of reward functions. I think that's what this means, right? The most number of reward functions. Uh, and the most depends on the most depends on the distribution of the reward functions considered, right? So you know, maybe we may consider some type of reward function, and you know, a certain action would be you know, uh would be considered, right? Would be given more importance. That does make sense. And then distributional as I'll ask the model to, you know, elaborate on this. Let's see. Elaborate on this distributional assumptions impact optimality. Let's see what that is. Uh, what happened? So let's see. The optimality of our actions in reinforcement learning agents heavily depends on the distribution of reward functions. That does make sense, right? On which reward functions we consider, right? So the reward functions basically control the optimality of what is the most optimal action. This concept is explored to understand how different assumptions about these distributions affect which actions are likely to be considered optimal. Reward function distribution. Different results are derived on various assumptions about the distribution of reward function. Represent any general probability distribution over space of possibility reward functions. D-bound includes distributions where the reward values are confined within certain boundaries. Independent and identical distributed rewards. When reward functions are independently and identically distributed, okay, so when the reward functions are okay, distributed, I don't know what distributed means really. It means that each state's reward is drawn independently from the same probability distribution expression. For instance, if x is equal to uniform of 0 and 1, then rewards are uniformly distributed between 0 and 1 for each state. Okay. Okay. Then this IID, this in identical distributed assumption simplifies the analysis because it provides a uniform framework to evaluate the optimal probabilities of action. Okay. Degenerate actions focuses on reward functions. Significant influences the likelihood that certain actions. By understanding these distribution assumptions, we can predict and potentially influence the behavior of RL agents. This analysis is crucial for designing RL systems that behave as expected in various environments. Okay. So let's continue. Uh, right, and then we have illustrated example. Examples are provided to demonstrate how the optimality of functions can be determined on different. Show how some okay. We don't need examples. So we are this depend on the prior beliefs. Okay, the optimality of action depends on prior beliefs about the distribution of reward functions. Prior beliefs depend on prior beliefs of the distribution. For instance, left or right actions at state can have different optimal properties based on assumed reward function distribution. Okay, application to real world scenarios. Let's see what this is. The discussion is relevant for reasoning about the behavior of future. I'll just off my video because the charging is like very less. So I'll off the video. So application reward sinners. The discussion is relevant for reasoning about the behavior of future reinforcement learning agents whose exact reward function may not be known. Understanding the probabilities of certain actions being optimal helps in uh, understanding the probabilities of certain actions being optimal helps in predicting and guiding the behavior of these agents. Overall, the section aims to demonstrate that the optimality of actions is not arbitrary but can be systematically analyzed based on reward function distributions and other parameters. Okay. Providing a foundation for predicting and influencing the behavior of the other agents. Okay. So yeah, we are getting into a certain path here. Maybe yeah, we should probably analyze if this is the path that we want to go to. But I think yeah, I think for now we are under probably the right path. Uh, choosing the conclusion is probably that uh, from the action that the model takes, maybe we could systematically analyze what we could systematically maybe analyze the uh, you know like the reward function, right? We could probably analyze the RL agent of what it is doing and what it is of its behaviors, right? Based on the reward function distributions, right? So we could take in the reward function distribution and analyze the behavior of the model, which is again quite straightforward, I should say. Okay. So some agents, some states, given they give the agent more control over the future. Okay, let's see what this is. Uh, what is power? Philosophers may have many answers. One prominent answer is the dispositional view. Power is the ability to achieve a range of goals. Right. So this will just copy that. Mm. We'll just use a good new notepad and we will I'll just save it as you know optimal policies power. I'll just use something like that. Right. Let's see what other papers we have, right? Just to let's see. Probably I have them in the desktop, right? And probably in the desktop. Let's see. What is this paper to notes? Okay, yeah. So yeah, this is other paper about you know I think on the paper of symbiotic is the solution or something. Yeah, that's probably something. Podcast structure. And what else do we have? What else notes? Yeah, I'm sure I've like we have studied a lot of papers, right? I mean, yeah, it's probably in the other laptop that I have been using. So yeah, let's continue with this study. So in an MDP, the optimal value function captures the agent's ability to achieve the goal R. Therefore, average optimal value captures the agent's ability to achieve a range of goals D bound. Uh, Average optimal value, we have definition. Power. Power has nice formal properties. So let's see what this is. We have max of 1 minus gamma by gamma of functionalities of gamma minus E of S transpose into R. So yeah, maybe we'll ask the model to uh yeah, we'll ask this model to elaborate on definition 5.2. Elaborate definition 5.2, and I'll just paste this before. It's probably yeah, very bad. I'll send. Let's see if it works. If it doesn't, I think we'll just move on. So we have some distributed definition, might not be very relevant. Uh, right. Okay. So let's go through this section. Meanwhile, let's see if this works. Okay. So anyway, we'll go through this section 6.1. Keeping option 10 open tends to be power seeking and tends to be optimal. Certain symmetries in the MDP structure ensure that compared to left, going right tends to be optimal and to be power seeking. Individually, by going right, the agent has strictly more choices. Okay, so yeah, having more choices means the model is more powerful. Okay, well, more choices means probably means uh, achieving a wide range of goals. That is what that means. So actions A1 and A2 are equivalent at state S. Written A1 is uh, this A2. If they induce the same transition probabilities, if they have the same transition, I think okay. So yeah, if the probable transition probability is equal, then they are equivalent A1, A2. The agent can create states in this by taking actions equal to right at state star. States reachable after taking action. Sorry for that disturbance. So I think I do understand what this paper is coming to, right? What this paper is trying to tell us. I know it is saying that if you have optimal policies, if you have any optimal policies based on the let's say interfunctionality, it generally tends to pick options or perform actions through which it could have multiple options, right? It would generally tend to both it generally it'll like to have it likes to have more number of options, right? That is what I think this paper is trying to tell us, right? It generally tends likes to have more number of options uh, because of the certain metric calculations that we have did, right? We have calculated some metrics, right? So based on the MDP, the Markov destination process. So based on these processes, so we could say we'll write in this notebook. We'll write. I'll write it. Human policies tend to pick right? So and then also we'll write yeah, so this is the power, this is the definition power, and this optimal policies then I tend to pick actions that that give them more options, aka more power, right? So just save it. And then is there any other conclusion that we have? Let's see, let's what is this, the five, okay. And then yeah, so how to reason about other environments? Consider an embryonic navigation task through a room of with a vase. Proposition 6.9 suggests that optimal policies tend to avoid immediately breaking the vase, since doing would strictly decrease available options. Dictates where average optimal agents tend to end up, but not what actions they tend to take in order to reach their RSDs. Therefore, a care is needed. In Appendix B, environment in which seeking power is a detour for most reward functions. Since optimality probability measures median optimal value, while power is a function of mean optimal value. Measures median optimal value. Okay, so we have, oh, interesting, right? Median and mean. I'm sure you studied that in your high school. Optimality problem measures median optimal value, while power is a function of median. However, suppose the agent confronts a fork in the road. Action A and A hat lead to two disjoint sets of RSDs, DA and DA hats, is that DA contains a copy of DA hat. Theorem 6.13 shows that A will tend to be average optimal over A hat. Shows that A will tend to be power seeking compared to A hat. Such folks seem reliably reasonably common in environment with irreversible actions. Okay, so yeah, I mean, not very, not very. Okay, a good paper. I think we'll end this paper here. We'll end this paper here. So these are the conclusions. Yeah, pretty. Yeah, I mean, like really not not a lot of not we haven't yet figured out a lot. Of course, we haven't. So maybe we could use this to critique the idea of RLHF, right? So probably one reason why RLHF doesn't work, or yeah, or alignment techniques in general doesn't work. So let's get to back to this paper, the first paper that we have started with. This is the paper, and also we have reward hacking paper, right? Also reward hacking, define reward gaming, define and characterizing reward gaming. This is the paper that we have also been learning. We have been reading this paper too. Uh, from these people of Oxide. From here we got to uh, you know the paper on power seeking. From here we have got, so let's see the conclusion of what reward hacking is. So our work begins the formal study of reward hacking for reinforcement learning. We formally define hackability and simplification of reward functions and show conditions for the non-existence of non-trivial examples of this. We find that unhackability is quite a strict condition, as the set of all policies we never contains non-trivial unhackable pairs of reward functions. Thus, in practice, reward hacking must be prevented by limiting the set of possible policies or controlling, limiting example limiting or controlling optimization. Example is limiting. Okay. Okay, alternatively we could pursue approaches not based on optimizing reward functions. So probably, yeah, again, probably another critique of reinforcement learning. So we could probably uh so yeah, let's get to the discussion. Let's see the discussion and see if there is any and if there are any important points, right? What do we need for the most part? Conclusion, and then finite policy sets, non-trivial results. Yeah, let's come to the results. Let's see what we have at the results. Our results are aimed at understanding when it is possible to have an unhackable proxy reward function. We first established that non-trivial unhackability is possible when considered the set of all policies. You might imagine that restricting ourselves to a set of sufficiently good policies would remove this limitation, but we show that this is not the case. Okay, we might imagine that restricting ourselves to a set of We then analyze finite policy sets and establish necessary sufficient conditions for non-equality application. Okay, I mean, I think we have something here. Okay, so yeah, let's open a new notepad, just see what we have. And then I'm probably going to end this video. I'm probably going to end this video with with the final structure of the podcast, maybe of the research paper of where what we're going to do. All right, so I'll just type in something, just just see. All right, let's see. Let's see the introduction. From where decrease expected return. Integrity made possible to create an unhackable process by leaving some terms out of the reward function, making narrower, overlook finding. Uh, or you know what? I think for this video, I think this is going to be enough. We're going to I'm going to like let's see. Let's plan for the future, right? So let's plan what how we want the paper should be. So maybe we'll start with the introduction. The introduction. In the introduction, we are going to define the importance of building moral AI, right? So we are going to the importance of building AI. In fact, we have already wrote the introduction, and again we may do some tweaking here there. Uh, and not a lot. We haven't wrote like a lot. We have the introduction, and then what do we have? We have the and then we'll get to reinforcement RLHF, right? Or you know what? Let's go through this. Let's look at the structure of this paper. Now we're not going to cover it like completely. So what do we have? I have motivation for alignment, risk, causes of our misalignment, scope of alignment, objectives of alignment. We have learn from feedbacks. We have RLHF. We have policy learning, scalable oversight. It may be not a lot to consider. Um, maybe we could consider this. Maybe we could add in there here and there. But I think we could continue with RLHF and other techniques. So we'll continue with we'll put in RLHF there, right? We'll sorry, not that, right? That is not the uh, right. So this here, and then we'll put in RLHF there, right? The idea of RLHF, reinforcement learning, using reinforcement learning to make to fine tune our model using our reinforcement learning on based on a reward function that we will train on that understands human preferences. So we'll put in RLHF there, and then maybe come up with this paper that we have read, that power seeking. We'll say we'll critique RLHF, or you know what? I'll just open that paper, the old paper that I've wrote. The old paper. I'll open it. Hide for floating media controls. Let's open the old paper. This is the old paper. Let's see what we have. Introduction. We have RLHF. I wrote about RLHF. Then limitations also we have wrote, right? Okay. So yeah, maybe we could just put in all of this, right? And then we also RLHF, RLAIF. Maybe we could do this, and then after this, after RLAIF, and probably also after safe RLHF, right? We'll put in all of our RLHF things. I'll just put it here: RLHF, RLAIF, and safe RLHF. We put in all of this, and then after that we'll have the critique, which is reward hacking, and then we'll have and also we'll include the power seeking thing, right? So yeah, up to here, maybe, yeah, I mean, again, these parts are all already pre-written. I've written all these parts, so we are just going to like finish the other parts, right? So after we have this power seeking thing, and then also, and then after that, uh right. So after that, so what should we have after that, right? Let's go to this paper. After that, what we have DPO, direct preference optimization. Maybe we could just directly include DPO, and we include DPO, constraint DPO, counterfactual DPO, right? These three again we could uh put it there. So yeah, again we'll put DPO, uh counterfactual DPO, I think. Yeah, counterfactual DPO, contrastive DPO, contrastive DPO, and also other techniques also, right? I do remember some other techniques. Uh, I think some other techniques might also be pretty interesting to put in there, right? I'll just say other alignment techniques, right? I do have a list of some alignment techniques I will consider. And after that, covering all these alignment techniques and also critiquing them, critiquing only these two, critiquing, right? After doing this, maybe we could have, right? After that, maybe we could, cover the, uh, let's say, disadvantages of alignment, or what should we call it, right? Probably, what is that? What is the right word? Maybe I've used it here. So let's see. Limitations. Yeah, limitations. Limitations is a good word. So it's a limitations of alignment techniques. We should probably come to try to understand some of these, find some other limitations from maybe on other resources, right? We will do that. And after specifying the limitations, and then we'll come to the idea of be making a actually conscious. We'll try to understand what consciousness is. And after that, is there any papers like, yeah, we have conscious AI paper, right? We have conscious AI paper. Other point of view of building more AI, building conscious AI. Again, here, after that, okay, this is the other point of view. And then we'll define consciousness. We'll define consciousness. And then after that, after defining consciousness, we'll try to understand different way of attaining consciousness. And okay, after defining, maybe we could say we could limitations of GPT, or limitations of transform models, or before that we could have like ideas of building consciousness. Yeah, so we'll different paths, or different, let's say, different ways to, let's say, different ways to attain conscious, to make AI conscious. Again, I think the most important one is the symbiosis one, and then also the paper, right, on liberal democ no that paper, that some people on the top should not control AI, right? We also have that. And I'll probably put that here also. Yeah, after that, after limitations of alignment techniques, uh the disadvantage of alignment technique. Making AI our pet. I'll just put in there just to make sure I remember. Making AI our pet. um And after that, after the dismissal alignment techniques, and after this, we will come to the other point of building conscious AI. After that, we'll define consciousness. We'll find the different ways to make AI conscious, and limitation of transform models to make our make our AI conscious, right? And then after that, maybe after that, if there is anything again, we'll add anything. I don't think. I think yeah, maybe we could try the conclusion here. So this is the overall a very high, probably very high level, uh, a high level structure. Again, a lot of part it is also it's pre-written. I have written it beforehand. So we have all this finished. We have all this finished, and also other element techniques we should write, right? And then the other things also we will write. We also have collected research papers, pretty relevant research papers. So yeah, I think that's it for this video. I'll just save this as the making AI morally conscious paper. Moral paper. Structure. I'll just put like that. So I think yeah, that's it for this video. And yeah, please follow me through this journey. And if you have any suggestions, please do share it in the comments. It will be a huge. It will be very valuable for me, a huge asset. So yeah, thank you for watching this video, and I will see you in the next one.